Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will obtain a formula for a confidence interval for the expected value of y. To be more specific, for the expected value of y0, okay, given x0, this x0 represents a set of specific values for the predictor variables in our model. Now bear in mind that now we're talking about multiple linear regression, so we have more than one predictor, so x0 represents a vector of particular values for each of those predictors. Okay, and we want to provide an estimate of that expected value of the response at that particular combination of the values of the predictor variables. Okay? Okay. So, before we do this, before we obtain this formula for that confidence interval, okay, let me remind you about a couple of results that we have talked about before, but that will be useful in the derivation we're going to about to discuss. Okay. Okay. So let me define a couple of elements here. A matrix of constants A with dimensions. It will be very important to keep track of those dimensions. So A is, as I said, a matrix of constants. Matrix of constants. Then we're going to have Y, which will be a matrix of, well, a vector, right? A random vector of dimensions m by 1. So random vector. Okay, and what else? No, that's good. So now let's talk about the expected value of A times Y. Okay, so we know that it's similar to what we have seen before with random variables. You get to factor out constants. In this case, you get to factor out a matrix of constants. That's one of the results I wanted you to remember. And the other one has to do with the covariance matrix. Okay. Another thing that I want you to bear in mind is that this expected value, right, is now a vector, right? And note that the dimension of that expected value will be m by 1. Okay, so m by 1. Okay, so now let me remind you about the covariance matrix of this transformation AY, right? We know that what we have to do before, when we had random variables, you would have the variance of A times Y. You would have that would be the same as A squared times the variance of Y, right? If you factor out that constant when dealing with random variables, all you have to do is you pull it out, but you square it. Okay. In this case, we have something similar, right? You pull out that matrix of constants, then you have the covariance matrix of y, and then you post multiply by the transpose. Okay. Now note that in this case the dimensions of the covariance matrix, what we're going to have is m by, right, what you have here is m by m, right? Oops. M by M matrix, right? Because this guy is going to be M by N, right? This guy, the covariance matrix, it's going to have the same dimension as this guy, right? N by N, and then this one, A transpose, is going to be N by M. So in the end, this covariance matrix is going to have this dimension, M by M. Make sense? Okay. So now that we have that result, let's talk about what we want. About the main result that we want to discuss here. So we want to derive this formula for a confidence interval, right? Bear in mind that confidence interval in general has the following form, right? Let me say this. We know that in general a confidence interval looks like this. It's an estimate plus minus a margin of error. Margin of error. Okay. So first, let's talk about our target. Okay. So our target is estimating that expected value. Okay. So let's be very clear about the model that we're going to be discussing. So the model, okay, we have y equals x beta, y equals x beta plus epsilon. Okay. Now let's talk about the dimensions of these guys. Again, in this case, what we have is a vector n by 1 n by 1 vector. Okay, this is a vector. What else we have here? We have x is going to be a matrix, our design matrix. And our design matrix, it's going to be, if we have k predictor variables, it's going to be a matrix that has dimensions n, right? It's going to have n rows, just like this guy, but it's going to have k plus 1 columns, right? So we have k predictors and one column of ones that corresponds to, you know, that beta 0. to the intercept. Okay, and well, we also have the beta. That vector is going to have those parameters, those unknown parameters, and it's going to have the following dimensions: k plus 1 by 1, right? And we also have, of course, epsilon, which is our vector of random fluctuations, and it will have the same dimension as our vector of observations, m by 1. Okay, so anyway, even when we see this, what I want you to keep in mind is that now we have vectors and matrices involved. Okay. Each of the elements of the vector epsilon, the epsilon i's, we know are assuming that are normal with mean 0 and variance sigma squared. Okay, so same as before. Let me write that down here. Epsilon I, we have a normal, mean 0, variance sigma squared, and of course we're assuming independence between those epsilon i's. Okay, so now what's next? We were saying we would like to derive something like this, an expression for the confidence interval of the expected value, right? So let's talk about our target. Target is this. We want the expected value at a particular set of values x0. So because remember that x0 now represents a vector. So let me use the following notation. X0 transpose will be the following vector. It will be 1, comma, x1, let me do it like this, x1, x1 1, comma, x1 2, or let me change this to make it consistent to that 0 that we are using here. You'll see that it makes sense in a sec. Okay, so what I mean by this, what we said is we have k predictor variables, right? So I'm using that first subscript to keep track of the observation I'm talking about, and the second subscript to keep track of the predictor variable I am referring to. So in this case, that one is for that beta 0 that we have in our model, the y-intercept, if you will, an extension of that. This again, it's going to be the value that multiplies beta 1. This is going to be the value of the predictor variable that multiplies beta 2, and so on up to beta k. Okay, so as you can see, this guy here is a 1 by k plus 1 vector. Okay, so the thing is, note that for a particular, right, y0, meaning the response evaluated at a particular value of x0, which is a vector, right, a particular combination of values of the predictor variable, what we have is something like this. Okay, I'm going to write this down in a detailed way. Beta 0, right, plus beta 1, oops, times this guy here, plus beta 2 times this guy, plus dot 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 plus beta k this is a k, this is a k as well, right, plus, and let me call the particular random fluctuation for that guy epsilon 0. Okay, makes sense? So that's just the same as this, but we're writing this down for a particular value. So this is just you know, one, a 1 by 1 object, right? It's a scalar. Okay, but now note that what we have here is just a, you know, a linear combination. It's just a multiplication. You could express this as a multiplication of that vector x0 transpose, right, times your vector of parameters beta, right? Okay, now if we take the expected value, which is our target, expected value of that guy, it's just the expected value of a sum. And expected value of a sum is the sum of expected values, and we know that by our assumptions, right? The epsilons are normal with mean 0, variance sigma square, so the expected value of epsilon 0 will be 0, right? Okay, so now this guy, as I said, we could rewrite like this, using matrix multiplication. Okay, this would be x0 transpose. It's a 1 by k plus 1 vector times a k by 1, a k plus 1 by 1 vector. So yeah, it makes sense, right? We can carry out that multiplication, And note something interesting. This is a 1 by 1 vector, right? Which means a scalar. And we can see it here, right? Okay. So just bear that in mind. Maybe I should write it down, that it's a 1 by 1, meaning it's just a number, right? But I want you to bear that in mind, that it's just a number in this case. Okay, so now that we have our target, that's what we would like to estimate. And note, in some textbooks you'll see that notation, like the one that I have here, that this is telling you that you are evaluating that response at that particular combination of values for the predictor variable. Okay? Okay. So if you want, we could add that here just to be consistent with our notation. Okay. So now what we said is our confidence interval is going to have that form, estimate plus minus margin of error. Let's talk about the point estimate. Point estimate. So let me talk about y hat 0. Okay, so it makes sense that y hat 0 is going to look something like this. Well, we just substitute these betas by, estimates of those betas, estimates of those quantities, of those parameters. Make sense? And of course, then what that means is we could re-express this as follows. Just that vector x0 transpose times beta hat, right? Where beta hat is going to have these dimensions, k plus 1 by 1, right? And this one dimensions remain unchanged, and then we end up with a 1 by 1 vector, which is then just a scalar, right? Okay, so that's going to be our point estimate of our target. Okay, okay, so that means that now what we need is to obtain that margin of error. Okay, but before we do that, right, let's see what's the expected value of this point estimate of ours. So the expected value of this guy is just the expected value of that sum, which is the sum of expected values, and we know that we could re-express this as a matrix multiplication, right? Okay. So now this is the part where our result will be useful, right? Remember that result we talked about here? We have a matrix of constants times a random vector. We want the expected value of that multiplication, so we just pull out that constant. Okay, So that's what we're going to be doing here. Then this is just x0 transpose times expected value of beta hat. Okay, but now you remember that the expected value of beta hat is just beta, right? So what we have here is x0 transpose times just beta. Right? So what we know here is that the expected value of our point estimate is going to be x0 transpose beta, meaning our target. So it's going to be an unbiased estimator of that quantity we're interested in. Okay, so to obtain that margin of error, we must have an idea of the variability of our estimator, right? So now what we have to do is try and find the covariance of this guy, of y hat 0. Okay, so let me write that down. That we need now. Let me copy paste this. This is what I want. I need the covariance of our point estimator. Covariance matrix of that guy. Okay. Again, this is where our result, the one that we mentioned at the beginning, the second result, will be useful. Okay. So now we have a matrix times a random vector. So we pull it out. Then we have covariance of our random vector times the transpose of that matrix. Okay. So let's do that. Covariance of beta hat and we have the transpose of that guy, which is just going to be in the end x0. Okay, are we good? Okay, so now we have to remember what's the covariance matrix of beta hat. Okay, let me go back to the other page so we can find it. So first, remember that beta hat looks something like, remember what beta hat looks like? So beta hat is just x transpose x inverse x transpose y, right? So let me write that down here. X transpose x inverse x transpose y. Okay, so now what we want is, you know, the covariance matrix of this guy. So let me write that down. Let me copy paste this. It's going to be useful. Covariance of this guy. It's going to be just the covariance of this. But see this here, X transpose X inverse X transpose. We could think about that as a matrix B of constants times Y, right? So using this result here, what we're going to have is just this guy, X transpose X inverse X transpose, times the covariance of our vector Y times this guy transpose. Make sense? And then we just have to do a little bit of algebra. We know that the covariance matrix of Y is going to be sigma squared times the identity. Okay, so let me substitute that. Sigma square times the identity. This is a constant, so we get to pull it out. Now, when we do this product and then find its transpose, what we will end up with is with X transpose transpose, which is just going to be X, right? Let me put it here and get rid of that transpose, and then we have this guy here transpose, right? Okay, so first identity times X is going to be X, right? So what we have on the next line is just this. But then X transpose X times X transpose X inverse, what we are going to have here, this product will be just the identity matrix. Okay? So what we have here is sigma square times the identity times that. Now, we talked about this. We talked about this at some point, that if you have a matrix B inverse transpose, that's the same as B transpose inverse, right? So these guys now will switch places. We'll have a transpose here. We'll have an inverse here. Okay, and then when you do this, X transpose X transpose, you end up with X transpose X again, right? So you have this times the identity, that's just itself, and that's it. That's the covariance matrix for beta hat, X transpose X, well, sigma squared times X transpose X inverse, right? Okay, so let me copy paste this guy, we will need it. So we have x0 transpose times this guy times x0. Okay. Note that we're going to be able to compute that product. Okay, it's going to have the right dimensions. So this is a constant, so we can pull it out. Let me just place some parentheses here. But yeah, you can see that what we have here is now the same as this. Sigma square times x0 transpose times x transpose, x inverse times x0. Okay. Oops. Let me just place that there. Let me remove those brackets. Okay. Now I want you to pay attention to the dimensions of this guy, right? So x0 transpose is this. It's a 1 by k plus 1 vector, right? This x transpose x transpose, right? X transpose is going to have dimensions k plus 1 by n, right? So in the end, x transpose x is k plus 1 by k plus 1, and then x0 is k plus 1 by 1, right? But what I want you to see is that in the end, this will be just a 1 by 1 matrix, right? So let me just write that down. Note that, and I'm going to write the dimensions of this guy. x0, no, x0 first. Is a, we have it here, k plus 1 by 1, is k plus 1 by 1 x0 transpose is, oops, is 1 by k plus 1, right? And this guy here is just k plus 1, oops, by k plus 1, then this is 1 by 1. It's a scalar, right? Why is that important? Well, because then this covariance matrix turns into a 1 by 1 matrix. That's just a variance. That will be just the variance of that point estimator that we want. Okay, so let me just copy paste this. And let me just say that now this guy here, yeah, it is a covariance matrix, but a 1-by-1 covariance matrix. So it's just the variance of my point, of our point estimate. Okay, so we are almost there. Okay, we have our point estimate, we have its expected value, we have its variance. This guy is going to give us an idea of the variability. Unfortunately, we don't know sigma squared, right? So what we have to do is estimate sigma square, right? So estimate of sigma squared. So remember that what we said, what we said we're going to use as an estimator for sigma squared is going to be the mean square error, right? So let me just remind you that so sigma hat squared is going to be the mean square error. And let me remind you that the mean square error is given by the sum of squares for the error divided by n minus k plus 1. Okay, let me write that down. Sum of squares of the error divided by n minus k plus 1. Plus 1. Okay, and that the sum of squares for the error is just something like this. We have the all the epsilons, right? Well, not all the epsilons. Now we're going to have e's. Remember that we're going to be using e, the residuals, to estimate the epsilons, right? Okay, and then we want to divide that by n minus k plus 1. Okay. Okay. So another way of calling this is s squared. Okay. Okay. So finally, we said our confidence interval looks something like this: estimate plus minus margin of error our estimate, well, our target was this x0 transpose times beta, right? This will be our point estimate, right? Plus minus we have a margin of error, which is basically the variance of our estimate, right? Okay, so but the thing is, well, let me just remind you about something that we had before. Remember, we had this critical value times the standard error, right? Okay, so we are going to have a similar situation, and in a minute we're going to argue why this makes sense. Okay, so it's going to be a critical value coming from a t-distribution with n minus k minus 1 degrees of freedom, and let me just use this notation, alpha divided by 2 here. Okay, so the variance, right, of our point estimator is going to be this, but now instead of having this is the variance, right, but we need the standard error, meaning we need the square root of that guy. And since we don't have sigma, we have to estimate it. Okay? Makes sense? Now, think about it. Why that t-distribution, right? So we know that a t-distribution is a normal 0, 1 divided by a chi-square distribution. So you would have just, you could argue, right, that the following quantity, right, which is your estimate here, oh, yeah, so this, right, your x0 transpose times beta hat minus your target, which is x0 transpose beta, right, that you could argue it's a normal 0, 1, and then you divide by an estimator of you know, the variance sigma square. We're going to have a chi-square there, right, and then it's going to be by definition a t-distribution. That's similar to what we did in the simple linear regression case, right? That's why we had that t-distribution, that pivotal quantity, and then we just solved for this, right? Okay, so finally, let me show you. This is the formula that we had before, right, for simple linear regression, and this is the formula that we're going to have now. Instead of you know, using the notation sigma hat squared, we're using an s squared, right? But we know that that guy is just an estimator of the variance sigma squared. Okay, makes sense? And here in our lecture notes, we're using R for the number of regressors. Okay, it's just the number of your predictor variables. Okay, but you can see that it's the same. Okay. Okay, so we are done. We were able to derive a formula for the confidence interval for this quantity, right? The expected value of our response variable at a particular combination of values for the predictor variables in our multiple linear regression model. Okay, well, that's it. Thank you so much. Thank you for watching. Please take care and keep working hard. See you next time. Bye.